So now that it's 1:30 on this Apple clock, it's a very happy day, always to see a student defend a thesis, and I don't have much to say, except I will comment that the combination of simulation experiments and experiments on the orbit test bed, I think, are going to make Loom Lab a more interesting place in the next year or two, because we have seen earlier this week actual experiments, and today we'll see simulation experiments. It occurs to me that actually there's some experiments maybe we'd like to do in both environments. So anyway, let's move on.
So hi everyone. My thesis is from the model on wireless network simulation. So I'll first talk about motivation behind the thesis and objectives. I'll talk very briefly about AODV with PHY Layer, and then I'll talk to current modeling in NS2, and then I'll talk about our modifications, and then I'll show the differences, what the difference it makes, and then hopefully I will conclude the talk. So today, this wireless net, the most common tool in wireless networking research has been simulation. Wireless network simulations differ considerably from wired networks because they have to model the physical channel properties like fading or interference, which have really profound effect on networking performance. However, it's almost impossible to replicate these properties inside a computer model. So they have to be statistically or otherwise approximated. There is again another problem. It's hard to adjust the level of detail when doing this. So if you fail to properly capture the first order factors, you'll get incorrect results. But if you put too much detail, you will increase the runtime of simulation, and maybe there won't be any changes in results. Monarch extension in NS2 has achieved this to some level, and our purpose is to take the modifications one further step. And as they did, due to its popularity, we just focus on 8.11b. 8.11b, actually, in the protocol, it uses infrared, DSSS, and FHSS, but in practical, it just uses DSSS. In DSSS, there are 4 modulation types. For 1 megabit per second, it's DBPSK with 11 chip Barker spreading sequence. For 2 megabit per second, it's QQPSK with 11 chip Barker spreading sequence. For 5.5 megabit per second, it's complementary code keying. 4 bits are encoded into 8-chip code word, and 11 megabits, 8 bits are encoded into 8-chip code word, so there is actually no processing here. This is the network stack of a mobile node in NS2. So, when the source has a packet to send, it first sends it to routing, and then when the route is found, the packets are headed to link layer. Also, link layer works with ARP, address resolution protocol, which maps the IP addresses to actual MAC addresses, which are put in the MAC layer or MAC header of the packets. When going up, AODV just gives them to link layer, and then it goes to the node entry. This is just a convention for in the code, in the NS2 code. In that, it goes either to source, to sync, or routing agent, and then if it's being forwarded. Of course, there is some multiplexing here, but that's not our issue in here. Also, the interface queue gives priority to routing protocols, routing protocol packets. MAC layer is 8.11b with DCF, both CSMA and CTS. And we did our modification in 8.11 MAC and network interface. This is the actual PHY layer in the code. Channel is not actually doing any physical layer manipulations. So channel actually does, when a network interface transmits a packet, it's passed on to the channel object. The channel object computes the propagation time from the transmitter to every receiver, and then it schedules a packet reception event at that time. And then when this schedule, when the SINR expires, it notifies the receiver that the first bit of the new packet has arrived. When the first, like here, so it's here. Now the packet is here. Before going upper layers, it goes to a radio propagation model, and then it computes the receive power, either by a free space model or two-way ground model, depending on which of them are smaller. And this power in standard NS2 code, this power is compared to two thresholds. One is carrier sense threshold and the other is receive threshold. If this power is less than carrier sensing threshold, this packet is discarded as noise. It's like it never occurred. Carrier sensing threshold is also used for CSMA when CSMA in the transmit state machine. Receive power is actually the receive power from a given distance D0, and D0 is actually the transmit range of the nodes. And it's independent of the signal modulation and transmit data rate. When this power, if this power is higher than carrier sensing threshold, but lower than receive threshold, it's sensed. But it's lower than receive threshold, therefore it's out of communication range, so it's discarded. If it's higher than receive threshold, then it's handed to make layer. In the make layer, assuming for example if the make layer was in idle state, when this packet comes, it switches into receive state. And then if another packet comes, which is also higher than carrier sensing threshold, and if their power ratio is higher than 10 dB, meaning the packet currently being received is 10 dB higher than the new packet, there's no problem. If it's not, the model switches in the collision state and it stays in that state until the longest packet ends. Like it might be the currently received packet or the new packet, whichever is longer. So, oh, by the way, I forgot. We call our model NS2MME because it stands for Modified Monarch Extensions. In our model, we took a very well-known simple SINR interference model. Node J employs transmit power Pj, and Gij denotes the power gain, which is actually either this or this one. And then at node I, the SINR is, this is receive power. Receive power from other nodes times theta. Theta Ij represents the fraction of transmitter J's received signal power that is projected onto the signal space. For example, if they were like orthogonal, this would be 0, for example. And plus the noise. This noise all includes both terminal noise and receive noise figure. We assume that there is no channel coding, so the detector makes hard decision on each transmit bit. At every node, total receive power from all sources, all active sources is computed. And then it's updated whenever a packet comes or a packet ends transmission. If we are receiving a packet with PR, the SINR is actually the same formula. It's theta times P total times the power of the packets being received. So this is just interference power plus noise. So, as I said, the total power is updated every time a packet ends or begins. So it looks like a staircase function in time. And assume that we are receiving this packet, and assume this is the SINR. For example, for this region, we call the segment, the region that the interval that the SINR is constant. So from SINR, depending on the modulation, we get the bit error rate, and then with that bit error rate, we compute the probability that all bits are correct, because we don't have channel coding. So if any of them are incorrect, it will be, we will decide that it has an error. So to see if it has or not, we throw a uniform random variable between 0 and 1, and this number is greater than PC, we'll mark this with error. And if any of these segments has an error, the packet will discard it. In order to correctly receive this packet, none of them should have an error. We also slightly changed the carrier sensing model in NS2. In standard NS2, carrier sensing is done by single packet power comparisons. So this is what's done in NS2, also in our model. So if there's a packet with PR higher than carrier sensing threshold, a timer is set to the end of that packet's transmission, which will tell you that the medium is busy in that time. Here, this is what we added. When the timer expires, McLaren checks if the P total from all of the sources is less than carrier sensing threshold. If it's not, the medium is indicated as busy. If it is, then you can switch into idle state and you can transmit or start your backoff timer. If it's not, you have to do the same check every time a packet ends to see if it's smaller than carrier sensing threshold. We also made a little change in the model called Preamble and header. In NS2, when the packet is considered as a single entity, so it doesn't matter if it's header or not. Like the header is transmitted in 1 megabit in NS2, it just accounts for the time that it's being transmitted. There's no other difference between, for example, reception model. So in our model, the first 192 bits, which are preamble plus header, we first check if the headers are received correctly. If it's not, we switch, the McLaren returns to the idle state, which is actually what happens in the protocol. Otherwise, you continue with decoding MPDU.
But if it returns to idle state, then it's going to start backing off and all that? Or
Yes, just like what it does in idle state.
but the channel is actually occupied by the rest of
Then it won't do anything. Like if the channel is still occupied.
it sees the channel is there.
Yeah, but there's a problem that it might start receiving another packet. If another powerful a packet with higher power comes, it might start receiving that packet actually. Like here, this was in error, and I switched in the idle state, and now here, at this point, another packet came, which has a higher power. It's a possibility that I can start receiving the other packet. That's the only difference actually.
So you think that's possible in practice?
Yeah.
And also possible in the model?
In our model, yeah.
Because POC has its own CRC checks, so it creates...
Yeah, there's CRC check here also, and of MPU. There are two CRC. When we did these modifications, we want our modifications to be comparable to NS2. For example, if we compare just NS2 without changing any parameters, it doesn't make any sense. Because the default power in NS2 is 24.5. And you can't compare this power, like it gives you actually a range of 250 meters. But in our model, if you set this power to 24.5 meters, it will give you like 550 meters range. So we tune the parameters such that they will always give the same range. For example, to do this, like we actually change the RX step. So now it's lower. So, we don't have anything like RX step. It's just noise floor and interference. And then carriage sensing chain also the same for both simulators. And range is also the same. And here you also see the ranges for high rates. So like for every different rate, standard NS2 also has a different RX step. So, like the explanation is here actually, with the range. Like as you a simple simulation at T0, nobody is at 0 and node 2 is at 100. And node 2 starts to move away from node 1 at the speed of 1 meters per second. The power is 10 dBn. At 10 dBn, like the transmit range of 1 megabit per second is 240 meters. So the dash lines are results of. By the way, this is done with using 512 byte packets CBR-UDP connection. The dash lines are modifications, and nonetheless, these lines are NS2s. So we actually, when we are doing the tuning, we fix the RX state such that it will just cut this in half. Like it corresponds to 10 to the minus 5 bit error rate or 512 packets. But if we repeat the same experiment with 1,500 packets, byte packets, we see that there's no change in range in NS2, but in NS2 the range is smaller because there's no coding. If you have a longer packet, it's much less likely to decode it correctly. And also it's the same for smaller packets. Like for example, if I don't have it here, but if you look at, for example, range of an RTS packet, it will be higher than standard NS2 in NS2 MME.
So what's the objective of this figure? Try to show that.
It actually shows the range. Like, so it starts at 100 meters. So this is 140 meters. So this is the range of 1 megabits per second in NS2.
But that's time on. It says time on the exact.
Yeah, it's time.
So it's actually, I think it's...
No, it's moving with one.
Oh,
so it's
moving.
Same thing.
Same thing. So it's actually the distance from the transmitter.
Plus,
yeah.
plus 100 meters.
Plus 100 meters.
So it's showing, like in standard NS2, the packet is transmitted fine until you get up to about 140 seconds, which corresponds to 240 meters. And then in the revised model with these, you calculate the probability bit error in every segment. You get it's almost the same, except it's not quite as sharp a clip.
So where does this difference come from?
Oh, there's NS2 is just doing hard threshold on received packets. We are doing SINR calculations, so it's.
But there's no interference in this case, is there?
There's noise floor. Here.
Here. Just 2 nodes.
So the noise floor.
So it's just competing against Gaussian noise, right? You, instead of saying, oh, there's an exact hard range, right? You get a kind of a cliff effect where...
Like even if interference is 0, like the SINR will be receive power divided by the noise power.
So at some point the bit error rate
theta is
not so good, and then the packet error rate goes to...
No, interference factor. Like it's the percentage of
noise at all.
Right.
the interference reflected on the received signal space.
When there are multiple flows.
Yeah.
So that's proportional to the number of flows?
Actually,
How do you calculate it?
this is really hard to calculate. We didn't calculate this. We made 2 different. We used either 1 or 1 over 12, 1 over 11, like 2 other sides of spreading. Like there is no spreading 1 and 1 over 11 perfect spreading, assuming.
So in your mobility case, the graph which you showed, did you consider spreading too? Or did you consider
Spreading is considered it's just like this. There is no other detail.
How about Doppler effect because of
Oh no, there is no difference in path loss model. We didn't change anything in path loss model. It's deterministic. If the receive power is some number, it's the same number until the end of transmission.
I understand you revise the formula to calculate the SINR. Do you maintain the same lookup table of SINR versus the which error rate?
We made 4 different lookup tables for each modulation.
So you just calculate the SINR. The SINR is for energy per bit.
Oh, that's different. This SINR is actually received power divided by received signal power. So this is not SINR per bit. So to get the SINR per bit, we also divide, for example, so this is SINR per bit for 1 megabit per second. This divided by 2 is the SINR for 2 megabit per second. This one divided by 5.5 is the SINR for 5.5 megabit per second. So like when you transmit more bits, the SINR per bit decreases.
So that's if you go to your plot, right?
This?
No, your next one. Your experiment with 2 nodes. The next one. That's why the range is shorter, right? On the higher data rates, right? Because essentially for the same transmit power, you have less energy per bit.
We also did another simulation with 4 nodes to verify our model actually. So nodes are distributed like this. Can you read these numbers? I guess you can. So node 0 is at 0, node 1 is at 50, node 2 is at 340. These are all stationary. Node 3 is at 400 meters, but it starts at T0. It starts moving with 1 meter per second away from node 2. In this experiment, the power was set to 10 dBm. Carrier sensing threshold was minus 81 dBm. So carrier sensing range is 284 meters, which means that node 2 and node 1 cannot hear each other. There are two same receivers actually. Packet size is 512 bytes. Rate is 1000 packets per second. It's just to saturate the channel actually. So when the simulation begins, for example, let me show it for 1 megabit per second. In standard NS2, when this node starts moving away from, the communication is okay until this is 180. 180 plus 60 is 240. So the range was 240 and it's again 240. It didn't make any difference. But in our model, because of interference from this transmission at here, the range actually drops to 160 from 240. Like a transmission like away like 290 meters drops the range from 240 to 160 meters. The same explanation, actual explanation is here. Power of interference from node 1 at node 2 is minus 81.45 dBm. At T equals here, like 110 for example, the received power of node 3 at node 2 is minus 72.17 dBm. So this corresponds to 9.2 dB of SINR. So when you look at the bit error rate of dBBSK, you get 10 to the minus 4. And assuming 512 by packets, the packet error rate is 0.3, which is actually very high. So the correction is lost here. The same explanation holds for the other data rates as well.
So in that range, the red one, right? Between 120 and 180.
There's no
this
communication.
Actually, no. In the case of original NS,
This is, yeah.
it actually just sees the difference between the received powers, received signals.
It doesn't see this anyway. Like in NS2, it doesn't hear this communication. It doesn't matter if it's there or not, because it's not in carrier sensing range of this node.
So why does it get that? I'm a little confused about how it gets that throughput.
NS2, you mean?
How NS2, original NS2, that throughput is in node 0 or?
Oh, sorry. It's throughput of node 2.
Of the transmission from 3 to 2.
Yeah,
It's what
this one.
should be getting.
So I should have said that before.
No, that's fine.
For this model, how to define the theta for each node?
Our theta was just one here.
Just one.
Yeah, we didn't do anything with theta.
So you will see the motion all occurs in one dimension.
Yeah, it's just one
But
dimension.
here you assume the node 1 and node 2 cannot hear each other.
So they are they have transmissions at the same time. But in NS2, you don't care about this because you don't hear it.
So for that, you cannot hear that. So the total power we compute, total power is the node 1, node 2, node 3, node 0. But you can't receive node 1, the node 2 cannot hear the node 1. So there are no interference from the node 1 to the node 2.
The regular original NS2 or the modified?
Model, yeah.
In the modified? So in the modified, you can't hear it, right? It's below carrier sense, but the interference is there.
We still account for it.
And
It
it's
doesn't matter.
accounted for in the calculation of bit error rate and then packet error rate.
So the next stage is we did experiments with DSR and AODV. Both are on-demand routing protocols, but they have some differences, and this leads to signal performance. DSR is basically just source routing. The source is in the packet header. It doesn't use tables. Route discovery is used just on-demand unit as a route to the destination. Route maintenance is done when the link breaks. Route discovery, it's just basically plotting. Intermediate nodes add itself to the path in the message and then forwards broadcast the message toward the destination. And it repeats again. When the destination gets this, it unicasts. This is important. Unicasts the route reply message to the source. And in the packet header, in the IP header actually, it will have all the path. When this is being done, if other nodes hear this transmission, can decode this transmission, they will also update their caches. And if an intermediate node during this route discovery has already have a route to the destination, it will send back the reply directly without waiting. Route maintenance in NS2, actually there are other ways of detecting link breakage, but in the NS2 it's done by X. So if you don't receive X for 7 times in a row, the link is broken. Route error message sent to the source of the message. Intermediate nodes, again, they listen to this. If they can decode, they will again update their routes, and source will delete the route. And if it has another one in the cache, it will try that. If not, it will route request, and when doing that route request, it also piggybacks this route error again to help the other nodes if they hear on the way. They will also update their caches. AODV is a hop by hop protocol, which means that every node just knows the next hop, and it's based on tables. It's also almost has very similar route discovery, and route maintenance, the idea is also very similar. Route request is again flooded, same thing. It's broadcasted towards destination. And when it's going towards destination, the other nodes make up the backwards route to the source. Destination, again, unicast route reply to message. Two different things here. One is sequence number. When you do a route reply, you always, there is a sequence number in the route reply. You always increase the sequence number. So this is for the source to decide if how old is the route, for example, if it's fresh or not. And create next up destination. And I hope count field is incremented also. If source has multiple replies, users require me to low subcount. So this is, I guess, what I explained. Intermediate nodes also may return route reply if they know that. But if source gets this message, it has to check if this is fresher than my route request. If it's equal with lower hop count, I can use it. But if it's same with higher hop count, I won't use it. Also, another difference from DSR, very important difference, is routing table entries are assigned lifetime. So if they are not used for a time, they are deleted. Route maintenance is again done by link layer X. Detecting node may attend the local repair. Local repair is done by, if you are closer to the destination, you do a local repair. If you are closer to the source, you'll just send back the route errors. And route errors is sent through every node, every path that was using that broken link. Notice that in DSR, that broken link information is not propagated to all caches. In the simulations, we use the well-known listed traffic and mobility models, which were used in Maltz paper, Perkins paper, which is, we use random waypoint models. The topology is again the same. We use 50 nodes. We use either continuous mobility or non-mobility. We use 512 byte packets or 1500 byte packets. Performance metrics are also the same as in those studies. Packet delivery ratio, this is defined for only CBR, is the data packets delivered divided by data packets generated by the CBR service. Goodput is the general definition of goodput. Amount of act TCP data divided by time of the highest received TCP act. But if not all the packets are received during the simulation time, then I divide this amount by the whole simulation time. Normalized writing mode is the routing packets transmitted per data packet sent to the destination. When doing this, we also count every forwarded packet. And if normalized routing mode also tells us that it has a correlation with the link breakages. So we did our first simulation with at 1 megabit per second. This is only a simulation that we look at the effects of theta, the interference factor. To see it more clearly, we turned off RTS-CTS option. There's continuous mobility, 15 source destination pairs randomly chosen with 512 byte packets at a rate of 3 packets per second. Simulations are run for 500 seconds. Each data point is average of at least 3 rounds with identical traffic scenarios but randomly generated mobility scenarios. All nodes have the same power in a single scenario, but as you see, it's varied from 10 dBm to 24.5 dBm, which is the default power setting in ASP. So these are the results. let me explain. For example, can you read this at all?
No, that's okay.
You can read it if you're close, so if you want to read it, you should move forward.
Okay, so at high power levels, there is actually no difference between NS2 results and NS2 MME results. It makes sense because when the power is high, the carrier sensing range is higher. So you don't observe many multiple simultaneous transmissions. So there is actually less interference, so that doesn't make any difference. But when you decrease the transmit power, the carrier sense shrinks, which leads to multiple instantaneous transmissions. We account for them. However, DSR NS2 doesn't account for anything outside carrier sensing region. For example, we see that AODV is not really sensitive to PHY layer in the simulations because it's not really affected by interference because of the timers that I mentioned and because of it looks at the freshness of the route. However, DSR aggressively uses these caches, and it often happens that it might get a stale route from a cache. This is the result for DSR with NS2 NME with spreading 1/11. So we see that it's actually better than NS2 results, which we would expect. And this is the result with our model without any spreading. And these are the corresponding routing laws. When this was done with carrier sensing threshold is equal to minus 84 dBm. Then we change the carrier sensing threshold minus 81 dBm. You see some differences. For example, the difference is that when you increase carrier sensing threshold, carrier sensing range shrinks again. So there are again more multiple transmissions, instantaneous transmissions. So in NS2 MME, this degrades the performance. However, in NS2, this improves the performance because you have more transmissions and also you don't care about the transmissions outside carrier sensing range. You can also see it in routing loads, for example. Like in in our model, the routing load increases.
So your point is it's a false improvement?
My point is you can't, if you have an idea about carrier sensing threshold, like you want to show, for example, you are trying to find optimum carrier sensing threshold. If you do your experiments, if you try to prove your results with NS2 NS2, standard NS2, it doesn't make any sense. That's the basic point. So this is the next is an explanation of this huge difference between DSR and AODV. We see that DSR demonstrates significantly lower routing load. These are DSR's routing load, these are AODV's routing load than AODV. Because, as I said, it uses caches, but using these caches actually destroys DSR. However, in a previous study with NS2, this was by Johnson, like who created DSR actually. It was found that 55% of the route replies were found from the caches, and 41 of them were actually based on broken routes. And they claim that DSR route maintenance was still able to perform well. And our results are different. Also, this is what I just said, carrier sensing threshold. The smaller the carrier sensing range, the better special we use, but the interference at the receiver can also increase. And you can see this with NS2. Then we switch to higher data rates. The scenario is exactly the same. However, we didn't use any spreading. And then we did the simulation with both RTS on and off. And then we just used two different transmit levels. transmit power levels, and we changed the packet rate from 4 packets per second to 10 packets per second, which corresponds to a total buffered load of 240 kilobits per second or 600 kilobits per second. Also, when doing this, all broadcast packets, MAC control packets, and data packets were sent at the same rate as, like the same rate was used for all packets. For example, so here we see the results for 2 megabits per second with RTS/CTS off, and here we see the results for 2 megabits per second with RTS/CTS on. The main difference is actually we see that RTS/CTS actually degrades the performance. Well, that's what we observe, and it's first with NS2-MME. But however, we see that there is actually, the difference is almost the same with the results of NS2 and NS2.MME. So this means that the difference is actually coming from the transmit power. It depends on the transmit power. When we increase the data rate, we see that there is a trade-off between data rate and communication rate. And for example, 5.5 megabits per second and 11 megabits per second perform almost the same. 5.5 megabits per second has a higher range but lower data rate. 11 megabits per second has a higher data rate but lower range. And because of that, in AODV's routing load increases with NS2-MME because the range is getting smaller. However, you can't observe this with NS2. And actually, the fact that it increases is actually helping AODV to outperform DSR. We also did some simulations with TCP. We used the base TCP model in NS2, which is based on PHY. This model assumes the packet has been lost just due to congestion because TCP doesn't know it is because of channel errors. Then it observes 3 duplicate X and when a retransmission time expires. We again use 50 nodes, but this time the power is 10 dBm. There is only one FTP connection in the network between 2 randomly chosen nodes. The file size is 10,000 packets. The simulations are repeated 50 times. And from the results, we made histograms for every different scenario. Here we see the results for results at 1 megabit per second with 512 byte packets. The range is 240 meters. So with 240 meters, we didn't observe any disconnected route. Like let me explain. This is the number of occurrences. These are AODV results, DSR results, and AODV results with RTS/CTS off, and DSR results with RTS/CTS off. This part is NS2, this part is NS2.MME.
What's your topology?
Topology is the same. 1,500 meters by 350 meters.
And random?
Yeah, randomly, but stationary nodes. So we see that when we compare the one half.
So for each experiment, you choose a new way to sprinkle the nodes into the box, or do you keep the same arrangement of nodes in the box for each experiment?
Oh, the distribution changes there.
The locations are
You
all...
randomly distribute it?
50 times, yeah.
And you average over it?
And then you randomly pick a pair. So you randomly distribute...
Actually, the pair is same. The
But they
distribution
get-
is...
yeah.
Actually, it's random in any case.
Right.
So it's an average of 50.
It's not average, like, we plotted the histogram to see it more clearly. Oh, we also have the averages here, if you can read it.
No way.
But what I was interested in is sort of clarifying sort of under what scenarios what do you observe. So maybe you put it.
So the first peak, the highest peak, corresponds to 1 hop throughput. We see that even at 1 hop, there is a difference between NS2 and NS2NM results. Like with 1 hop, you wouldn't expect anything to happen, but the difference is because in the route discovery, in NS2NM, the route discovery might take longer because of the collisions. That's the only difference.
But 1 hop, you should also take into consideration what is the distance between the two hops, right? In your case.
If it's 1 hop, it's smaller than 240 meters.
The data rate is 1 megabit per
Data is 1 megabit per second. When we turn off RTX-CTS, we see that the performance improves. When we compare this with this one, if you can see, the distribution is exactly the same, but the mean value is different. With RTX-CTS, the mean value is higher, which is expected. With 2 hops,
for a mean value of what?
Mean value of 1 hop throughput. Like the distribution is the same, but it's shifted slightly if it's visible.
Okay.
Like when you compare this with this has a higher mean value.
So the 10 on the y-axis means?
Number of occurrences.
That is, of the 50 flows.
Like of 50 measurements, 50 scenarios, the throughput was 0.5, for example, 7 times.
But all of them have 1 hop in that graph?
Here, just here.
It's only those. And how about the others?
Just come. With 2 hops, RTX-CTS improves the performance. For example, this is this throughput with off, and this is the throughput with RTX-CTS on. We clearly see that there's an improvement in both cases, whether you use NS2 or NS2NM. However, when you look at the average values, you can't really see any improvement. Because at higher hops, because of the overhead of RTX-CTS, the improvement is there's no good improvement. That will be and then we switch to 2 megabits per second. Basically, if you can't see an improvement in 1 megabit per second, you shouldn't be able to see any improvement at 2 megabits per second, because when you increase the data rate, overhead of RTX-CTS increases. So NS2 and NS2NM still agrees that RTX-CTS degrades performance. There is also a very important point. The performance of AODV is much worse with NS2NM. Like for example, you may see normalized routing load of 10 in some cases, which means like you send 10 routing packets to send 1 data packet. I will explain this later.
So when you plot these things, there's some discontinuity because of small sample size. Why didn't you?
This thing was
With on all of these, I mean, is it an intentional choice of sample size, or are you computation limited? Or, I mean, ideally you would like to see smooth distributions coming out.
actually, there is a jump between, if a connection is 1 hop, when you switch to 2 hop, you can't see anything
Yeah,
here.
so that's what I'm asking, that is it converging towards this even if I
Yeah, it will converge to, it will be like this.
Sample size, even this part,
Mhm.
first cluster will also have this shape.
Like first cluster may look like as a
That one is one
distribution,
one
but
unit, yeah.
still it will have peaks. Like it won't have just one peak.
So what happens there is if you like breaking the experiments of this like you always see the instances, right, of network configurations that are where the path is 2 hops, right? And then the rate is always something around 0.4, right? And the 1 hop path is always around 0.8, and he could do 500 experiments and he'll see this kind of histogram behavior, right? It depends on what kind of connection you get based on.
Yeah, I was wondering that if you keep doing this, you get some really smooth distributions around the 1 hop and 2 hop or more.
Yeah.
So maybe around
1 hop, probably they will be smooth, but it will be still be peaks.
Yeah, so when
Like
you
the overall distribution
I
won't.
understand. So from the point of view of presentation, is it desirable to have to run it as long as you need until you get the smooth plots, or is it customary to sort of draw?
Actually, we just did
somewhere
50 line.
Okay.
We don't see.
You're drawing conclusions from the height of these bars, the distribution of these heights, and that may, since it's a random experiment, that may depend on.
You isn't really drawing conclusions so much from the height of the bars, as much as
the one conclusion was RTS CTS improves performance, right?
It doesn't improve performance here.
No,
performance on the previous
I don't look at here when I'm talking about RTS CTS. I look at the mean values of 50 different simulations, and it should.
Then you need to know the confidence interval on these values, right? How do you know 50 is enough?
How do I know?
What is the standard? You have the standard deviation there?
Oh, yeah.
0.18.
So is that small enough to draw that conclusion?
Maybe not, but I think these charts are more valuable because of the conditional information they provide. Like what you see is, for instance, up in the upper right corner is, when you have 1 hop paths, right, those network instances, your throughput is always right around whatever that bar is, 0.8.
Sure.
Right? And it's always very close to, and then you go down in the other experiment, right, where you turn RTS, CTS off, and all instances of 1 hop path corresponded to, shifted to the right, you see, and if he did 100 experiments, right, maybe you'd get some distribution around this and some around that, but the shift is quite obvious.
Actually, there is a distribution. If I use a smaller bin, you will be able to see it.
Yeah.
But if you then form, for some reason, the total number of 2 hops is less, then your throughput may actually be reduced, even though, or if you just look at the 2 hops if you look at the 2 hops isolated, then
if you look at 2 hops,
improves throughput. But what you don't know is if the number of 2 hops has shifted. The number of 2 hops per hour versus 1 hop per hour versus
I understand.
3 hops per hour.
Yeah, it's funny, I always assumed they were the same, whether you use the RTS, CTS or not, right? I take it for granted that whether you have RTS, CTS on or not, that in each experiment you form a 2 hop or a 1 hop.
Yes, if you use RTS, CTS on, if it's on or off, it doesn't matter, because in the route discovery all packets are, except for the route reply, all packets are broadcasted, so there is no RTS, CTS in the route discovery. So it doesn't affect. Like these scenarios have exactly the same route discovery, except for the route reply.
But losses and route reply, could that affect your forming of route? Losses of route replies that occur because you have turned RTS, CTS off. You may be able to, you may be choosing longer routes because you lost more route replies, or these.
There's a
not so sure
possibility. Yeah, that might happen. But for example,
Remind me how many nodes are in these experiments?
50 nodes, just 1 connection.
50 nodes or 25 nodes?
50 nodes,
So, how many TCP flows are there?
just 1.
So, others are not active? Other nodes are not active?
They are helping the routing. Or not. They may be, has to be active.
And do you actually fix, how do you choose whether you want 2 hops or 1 hop or 3?
I can't choose it. I just look at the results. I didn't.
Route discovery chooses how many hops to get.
So I think Marco's point is valid that route discovery itself might change if RTS, CTS does a little bit of suppression of hidden node, then the number of the degree of connectivity would tend to decrease slightly.
Yes, that's okay. There's.
But maybe not a very big.
I'm not sure how it's negligible or not.
I would think that would be more an issue, like it'd be more likely in the routes with a large number of hops. So if you are following, if you think, oh, two nodes are very far apart and there's a lot of hops in between, there are a lot of potential paths, right? The route request,
it's likely that you will get
is more complicated, the number of replies is larger. Down in this thing, sometimes you might get 7, and maybe if RTS, CTS are off, maybe you'll get 6 or 8, possibly. You get more variation.
Actually, in that case, it's more probable that you will get the smaller hop response, because longer hop will be prone to more collisions when coming back to you.
Comparing with RTS, CTS versus not in that segment.
No, when you talk about if RTS, CTS is off, like when you are getting the reply with 6 hops, compared to 2 hops reply, the 6 hops is more prone to collisions. So I think it's more likely that you will successfully receive the 2-hop response. But there is, of course, a possibility that you might successfully receive, for example, 6-hop response. But I think it's negligible. I should look at it, yeah.
So in this particular experiment, your conclusion is that MME leads to finding more longer paths because there's more realistic noise effects?
No, it's not finding longer paths actually.
If you look at those big spikes around 0.
This?
No, and the previous one.
Oh, I'll come to this later. Actually, so this was with 512 byte packets. To see if RTCTs are compared with high bigger packets, we increase the packet size. So now we see that with NS2, RTS, CTS is actually improving the performance. Because when we increase the packet size, we actually are decreasing the overhead of RTS, CTS. So we see this improvement. However, this improvement, there is still improvement, and actually there is no improvement with DSR. It's not clear to, it's not easy to observe any difference between RTS, CTS off and on. So, what's the reason for this contradiction? To illustrate this, we designed 8 similar experiments. So experiments are designed such that all nodes will have exactly the same distance between them throughout the simulation. And then this distance will grow at 0.5 meters per second. For example, in the first one, in every one, node 1 is stable, node 2 is, in all experiments, moving with 0.5 meters per second towards here. So which means that this distance is growing with 0.5 meters per second. When we add node 3, it moves with 1 meters per second. So these distances are kept equal. The same thing holds for, like, for example, in this one, node 2 moves with 0.5, node 3 moves with 1, 1.5, 2, 2.5, 3, 3.5, and 4 meters per second. At T0, this distance is 125 meters, and at the end of simulation, we run it for 100 seconds. It's 175 meters, which is very close to the communication range of 2 megabits per second, which is 188.5 meters.
So out of those nodes, who's sending, who's receiving?
Sorry. Node 1 is sending to the furthest node. So like here, there are 8 hops, 6 hops, 4 hops, 2 hops. And in all these experiments, RTS CTS was turned on. So we are trying to show even if RTS CTS is on, there is a difference between NS2 and NS2 MMU. We plotted the latest sequence numbers. For this one, for 2 nodes, there is no difference between NS2 and NS2 MMU, which is expected, because there can't be any collision. For 3 nodes, there is again no difference. However, it's not real visible here, I guess, but the slope of the curve changes slightly at 34, when the time is 34. When t is 34, actually, after that, node 1 is a hidden terminal for node 2. Like after, like this 250 plus 34 is 284, which is the carrier sensing range. So after that time, these nodes cannot hear each other. So even if you have RTS CTS, RTS packets might collide. So just it slightly degrades the performance.
This is UDP transfer?
This is TCP. And there are 4 nodes. There can be only one interferer at a time. So node 1 and node 2 don't hear each other. When node 1 is transmitting, node 4 may transmit, and there might be a collision here. Or otherwise, there might be a collision at N3. So when there is a collision, because of the design of the scenario, this SINR is 12 dB. And when you look at SINR of 12 dB with 2 megabits per second, you get a bit rate of 10 to the minus 3, which is not enough to have a good packet error rate. We know that RTS packets are colliding actually, which are 160 bits. So packet error rate is 0.15. But however, of course, we don't see such a big difference because they're not always transmitting at the same time. To see this packet error rate, they have to be transmitting the packets at the same time. So we don't see that much degradation. When we increase the number of nodes, the difference, because the number of simultaneous transmissions increase, the difference gets bigger. However, for example, in NS2, the slope is almost constant, which means that every instance of the scenario, the channel's conditions are almost the same. However, when the nodes are getting further away from each other, you are both reaching the communication range, and both the SINR is dropping your communication code. So when we think about this, these scenarios were mobile scenarios. If we think about every instance of these scenarios as a mobile, as a stationary case, for example, assume that I made an experiment that I put the nodes 205 meters, 205 meters away from each other, for example, here. Sorry. They move it 0.5 meters per second, so this corresponds to 125 plus 40 meters, 165 meters. So we see that in NS2, there's no problem. But here, with NS2, the slope is very low. So here, you might actually see link breakages. Like there is actually no mobility at all, but you might see link breakages. So when there's a link breakage, routing protocol has to look for a new route, and then it will possibly find the same route again, and then it might again see that link breakage. This cycle may repeat. So what's important is if you have faster route discovery, you perform better, which that's the reason DSR performs much better than AODV because of DSR's aggressive caching strategy. When we look at the same graph.
So if I understand that, you're saying the routes are really fine, so DSR goes to a cached route, which is okay?
Yes.
Because the route was okay.
So we see that AODVs fail to find quick layer. For example, here, the normal routing load can be huge, but you can't see this with NS2. However, we don't see, even with NS2 enemy, you don't see this much degradation with DSR. For example, when we switch from NS2 to NS2 enemy, the normalized routing load with AODV, I'm talking about the mean values, increases 18 times with RTS CTS. 18 times. And 8 times without RTS. But it's usually less than 0.2 around here. I'm saying 0.2 because I know the beam size is 0.2. So it's usually less than 0.2, but some cases it can get as high as 10. So we see that when RTS CTS is off, this difference is smaller than the case with RTS CTS on. Because when RTS CTS is off, NS2's model is able to track the major collisions. When, like for example, assume there is no RTS CTS and this node 1 doesn't hear node 3 and they transmit at the same time. If a collision occurs here, since they are both in the carrier sensing region, NS2 can track this collision. So when RTS CTS is off, there is still difference, but the difference between NS2 and NS2 enemy is less. We can also see it from here. Like this is compared to the good slope relative to NS2. For example, when we switch from NS2 to NS2 enemy, how much it drops. We see that with RTS CTS on, the drop is higher. With RTS CTS on, it's smaller. And with AODV, in every case, it's much higher. We did the same experiment with 5.5 at 5.5 megabits per second. In this case, we saw that TCP sender receiver were disconnected in 12 experiments because the range is 150 and sometimes the good put for 12 experiments, the good put is just 0. And because we increase the data rate, we increase the overhead of RTS CTS. So in every case, even in NS2 MME or NS2 MME, RTS CTS mechanism is worse. We see the same thing even if we increase the packet size. Again, RTS CTS degrades the performance.
How many hops is this?
How many hops? Again, like this one is 1 hop, like 1 hop, 2 hops, and then these are higher hops because it behaves like 1/x. When you increase the number of hops, like there's no difference, big difference between 5 hop throughput and 6 hop throughput. But there is a huge gap between 1 hop and 2 hops. So in this talk we first presented the flaws in NST modeling and reasoning behind the modifications. And then by that 4-node scenario, we verified that in a simple model, we verified that analytically our model is correct. And then I showed you the differences. The differences, this is really important. The differences are not just quantitative. It's the behavior also. Like it affects DSR and AODV in different ways. Well, I also showed that CTS, like, and RTS-CTS threshold, for example, tunable parameters. If you are going to experiment with these, if you use NS2, it doesn't make any sense. For example, we saw that increasing the carrier sensing threshold increases packet level ratio in NS2, but decreases it in NS2 anyway. And RTS, CTS, we saw that in some cases they agree, in some cases they don't agree. So it's still, NS2's model is not good enough to draw a conclusion.